In early 2025, a team of astronomers pointed the James Webb Space Telescope at the Bullet Cluster, searching for the oldest light in the universe. Tucked deep in the background of this massive field, they found two faint red dots. By the gold standard metrics used in astronomy for the last 30 years, these two pinpricks of light appeared to be galaxies sitting at the very edge of observable time, recorded as they were just 100 million years after the Big Bang. Galaxies forming that bright and that early strained the math of the lambda CDM model to its breaking point. If these red dots were genuine, the discovery would force a total revision of how we believe the first structures in the universe assembled. Faced with findings that could rewrite textbooks, the team did something incredibly rare in modern cosmology. They didn't publish. They suspected a highly specific imposter was tricking the telescope, masquerading as a record-breaking discovery. So they kept quiet. They secured telescope time for a second observation and waited exactly 1 full year to take the exact same picture. This year of silence was the only way to execute a definitive test. The second image would prove whether they were looking at the dawn of the universe or something hiding much closer to home. To understand how a $10 billion telescope could be fooled, we have to look at the workhorse of deep space astronomy, the dropout method. This graph represents a distant galaxy's light spectrum. The intensity travels steadily, then plummets at a sharp cliff, the Lyman limit, where neutral hydrogen absorbs ultraviolet light. As the universe expands, this specific cliff stretches over billions of years, sliding into the infrared range where James Webb operates. For 3 decades, finding this specific infrared drop-off was the absolute guarantee that you were looking at an object from the beginning of observable time. In January 2026, the 1-year anniversary of the first observation arrived. The new images downloaded, and the team aligned the pixels with the original data. While the background remained static, those two faint red dots had clearly drifted sideways across the sky. Galaxies sitting 13 billion light-years away do not move visibly across our sky in 12 months. At that distance, their proper motion is effectively zero. With a single measurement, the original interpretation collapsed. These objects were not at the edge of the universe. They were hiding in our own galactic neighborhood. The dots were Y-class brown dwarfs, located just 1,600 light-years from Earth. A brown dwarf is a failed star, an object that never accumulated enough mass to ignite sustained nuclear fusion. They wander alone in the dark for billions of years, slowly radiating away their heat until they reach the temperature of a warm cup of tea. At these frigid temperatures, their atmospheres are thick with complex molecules, heavily dominated by water vapor and methane. This graph illustrates a brutal coincidence in physics. The methane and water in a cold brown dwarf absorb light in a way that overlaps perfectly with the red-shifted hydrogen cliff of an ancient galaxy. The universe produced an accidental homonym, 2 entirely unrelated physical processes, leaving identical spectral fingerprints in our data. The bullet cluster finding wasn't a fluke. Deep field surveys are littered with these local imposters. Many of the frantic headlines from the past 2 years declaring that the telescope had broken cosmology were actually fueled by these unrecognized brown dwarfs. This forces a new understanding of our neighborhood. The Milky Way is crowded with tens of millions of these invisible, freezing, failed stars. A sprawling graveyard of fossil objects drifts between the bright stars, cooling in the dark since before the Earth was formed. The real early galaxies are still being mapped. Astronomy is simply undergoing a rigorous period of cleanup and cross-checking as we learn to distinguish them from the background noise. This is the scientific method working as intended. It requires the patience to measure subtle sideways motion over years and the precision to gather high-resolution spectral data. Observation reveals a complex language where the closest objects and the farthest objects happen to wear the exact same disguise. The boundary between the cosmic dawn and our own galactic neighborhood is a fog. Only slow, careful science can tell us exactly what we are looking at.